Lesson 2-3, Friction. When two objects are touching each other, there's usually a contact force. The normal force is that contact force that's perpendicular to the surface, where the one object is holding the other object up. Friction is the contact force that is parallel to the surface and opposes the motion, wants to keep the objects from sliding across each other. And this comes mainly from the rough surfaces between the two objects. There are two types of friction. The first is static friction. Static friction keeps things from moving. What it does is it cancels out an applied force until the applied force gets too big. So in this first picture, the person is pulling with just a small amount of force, and the static friction is just small. They apply with more force, and the static friction gets larger. They apply more force, and the friction keeps increasing until it cannot get any larger. And then movement would begin. The size of the friction depends on the force pushing down and the roughness of the surface. So the heavier the object is, the more friction there is, and the rougher the surface is, the more friction. So static friction depends on the force pushing down and the roughness of the surface. So our static friction is less than or equal to mu, that is the Greek letter mu, S Fn. All right, so what is all that? Well, the more pushing down, or the normal force, or if you'd like, the apparent weight, normal force, the more friction there is. And the mu s is the coefficient of static friction. It ranges between 0.01 to about 1.5 for really rough. 0.01 for smooth, 1.5 for really rough. Once motion has started, there's no longer static friction, there's now kinetic friction. And kinetic friction equals the coefficient of kinetic friction times the normal force. So it's essentially the same equation as the static. The static, though, was less than or equal to, so it changed until it reached its maximum. Kinetic friction is always the same. The coefficients are different. The coefficient for the kinetic friction is usually less than the coefficient for static friction. It's harder to get something moving than it is to keep it moving. Let's say a car skids to a stop after initially going 30 meters per second. Coefficient of kinetic friction is 0.8. How far does the car go before it stops? Well, we need a car. And what forces are on this car? Well, there's weight pulling the car down. There's normal force on the road from the road pushing the car up. And then there's friction slowing the car down. So in forces, our main formula is F equals ma. So we're going to work in the x's and the y's. Let's start in the y's. If I say net force equals ma, in the y's I have the normal force up and the weight down. And our weight could be, was found with mg. Oh, but what is the acceleration in the y? In the y direction, the car is not accelerating. It is not flying up into the sky. It is not sinking down into the road. So in this case, our normal force equals the weight. Now if we go in the x direction and do net force equals ma, In the x direction, I just have my kinetic frictional force. But kinetic friction force is the coefficient of friction times the normal force. And there is acceleration in the x. It is slowing down. The speed is changing in the x. So we do have the acceleration. The coefficient of friction, it says, is 0.80. Our normal force from the y's was mg. I don't know the mass, but I could divide both sides by the mass. So if I put in 9.8 for g, I can find my acceleration. Which would be 7.84 meters per second squared. Now that I know that, now we can figure out how far it goes before stopping. All right, so for example, we have to go back for kinematics. We know our initial velocity is 30 meters per second. Oh, but we're initially going left. And so I'm going to call that negative. Our final velocity will be 0 because we're stopping. Our acceleration is 7.84. And we are accelerating towards the right. The friction is slowing it down, which is pointing towards the right. Let's say our initial position is 0. We are looking for a final position. So use the equation from kinematics. A was 7.84. So 30 squared would be 900. And 2 times the 7.8 is 15.68 times d. So subtract the 900. And divide. And we should get negative 57.4 meters for our displacement. Now why is it negative? Because those cars heading left. So it went left 57.4 meters. How far did it go? 57.4 meters. 65 kilogram skier is coasting downhill on a 15-degree slope. There's my 15-degree slope, and there's my skier. Assuming the coefficient of friction is that of waxed wood on snow. So we're going to look that up. And the textbook says that that is 0.1. What is the skier's acceleration? Well, what forces do we have? We have the normal force. We've got frictional force. Now remember, we're sloped. So let's say x is parallel to the slope, going uphill, and the y is perpendicular to the slope. We also have weight. But weight is going straight down. It's not parallel or perpendicular slope, so we need to divide it up in two components, so that we have the x component and the y component of the weight. So what is our angle? Turns out, if we use geometry, that's perpendicular there, and that's perpendicular there, so that is actually 15 degrees. the same as the slope. The x is opposite the 15 degrees, so it'll be our weight, and it's opposite, so that means we're going to use sine 15. The y is adjacent to the angle, so we'll use cosine. Now we could start in either the parallel or the perpendicular direction, either the x or the y. It's often easier to go in the y if we have friction because we need to find normal force. If I say my net force is ma, and the y direction I have normal force up, and the y component of the weight down. So minus our weight cosine 15 degrees. All right, we're given the mass of our skier. So weight is mg. And we have no acceleration in the y. We're not leaving the snow up into the air. We're not digging a hole into the snow. We're staying along the surface of the snow. So my normal force will equal mg cosine 15 degrees. Oh, I have the numbers. So I could plug in the 65 kilograms. G is 9.8. So put that in the calculator. And we get our normal force of 615.29 newtons. Now let's work in the x. Net force equals mass times acceleration. If I'm dealing with forces, that's the formula. And the x, I've got friction going uphill. In this particular problem, I'm going to call friction positive, because uphill positive. And then I've got the x component of the weight going downhill, so minus the weight sine 15 degrees. Friction is the coefficient times the normal force. Weight is mg. And we are accelerating, so I do need to have the ma still. The coefficient of friction was 0.1. The normal force was 615.29. The mass is 65. G is 9.8. Sine 15. Mass is 65 kilograms times A. So the left side of the equation becomes negative 103.34 newtons. Divide by the 65, and I get negative 1.59 meters per second squared for the acceleration. So the skier is accelerating negative, which means downhill, at negative 1.59 meters per second squared. While hauling firewood to the house, you pull a 100-kilogram wood-filled wagon across level ground at a constant velocity. You pull the handle with a force of 230 newtons at 30 degrees above the horizontal. What is the coefficient of friction between the wagon and the ground? All right, so you can see I have my free body diagram here. Forces on the wagon are the normal force up, the weight down, the friction. I have the friction going left. I'm pulling the wagon towards the right, so the friction's left. And the applied force is along the handle. And I said that is 30 degrees above the horizontal. Since we're doing forces, let's do net force equals ma. And I'm going to start in the y again so I can get the normal force, because I'll need the normal force to calculate the friction. So in the y direction, I've got the normal force up, the weight down. But I also have a portion of the applied force. I have that portion opposite the 30 degrees. So it's going up, so I'd say plus the applied force times sine, because it's the opposite of the angle, 30 degrees, equals ma. Let's find the normal force. The weight is mg. The applied force, let's see, how about our acceleration? It's a constant velocity, so there's no acceleration. The mass is 100 kilograms. G is 9.8. The applied force is 230 newtons. Put things in the calculator. It looks like my normal force is 865 newtons. All right, let's now work in the x. So net force equals mass times acceleration. In the x, I have friction going backwards. And I have the x component of the applied force going right. The x component is adjacent to the angle, so we'd use cosine of the 30 degrees. Friction is mu times the normal force. And it's constant velocity, so there's no acceleration. We're looking for the coefficient. Normal force is 865, which we got from the y component. The applied force is 230. So subtract the 199. And divide by the negative 865. And we end up with 0.23 for our coefficient of kinetic frictions. Kinetic because it's moving.